Hey everyone, I am Miss Hu, your physics teacher, and in this video, I'm going to show you the phenomenon of total internal reflection of light using a semicircular glass block.
Now, first of all, I'm going to explain why we use a semicircular glass block in our practicals to study total internal reflection. Yes, I am aware that what we have on screen here is a rectangular block. I need to explain light refraction first with the rectangular block before we go into the semicircular glass block. So let's say this rectangular block represents a glass block with which we will study light refraction. And by now you should already know what light refraction is. The light refraction phenomenon that we are familiar with is always observed when the light ray travels at an angle to the boundary of the glass block. So let's say this arrow represents the incident ray traveling from air into glass. Due to the different optical densities of air and glass, light will travel at different speeds. That means that when light travels from air to glass, the light ray will change direction because the speed changes. So light travels more slowly in glass, therefore the light ray will refract towards normal. And that's why we will see that there is a bend in the light ray. That means the light ray has changed directions. And then when light travels from glass to air, it will refract once again because the speed has changed. So this is the phenomenon of light refraction that you should be familiar with by now. Another behavior of light, which you should be familiar with by now when you're studying light refraction, is that when light approaches the boundary in such a way that it is perpendicular to the boundary of the glass block, that means the angle is 90 degrees. Hold on, the line is trying to snap to the center, which I don't want it to. So if the light ray were to travel in such a way that the angle between the ray and the boundary is 90 degrees, you'll find that there is no change in its direction. The light ray will continue to travel in a straight line all the way through to the other side. Let me just fix this a little bit so that it is more of a 90-degree angle. So why isn't there a change in direction? So we know that this angle is 90 degrees, but remember that the incident angle is always measured between the normal line and the light ray. So if we were to refer first to the first light ray on the left-hand side, this is the normal line. That means that the incident angle is this angle between the light ray and the normal line. So this would be the incident angle, which I'll label as I. The refracted angle is also measured between the normal line and the light ray. So this angle here, between the normal line and the light ray, which I'm labeling as R, that would be the refracted angle. So if we were to refer to the light ray on the right-hand side, you can see that the light ray is parallel to the normal line, because the normal line is a line that is perpendicular to the boundary or 90 degrees to the boundary. So now we've got a situation where the light ray directly overlaps the normal line. So if you were to measure the angle, how much do you think the angle is? So a lot of students always say, "Oh, 90 degrees." No. Remember that the angle is measured between the normal line and the light ray. So because they're parallel, they're overlapping over the exact same position. That means that the incident angle here is 0 degrees. Because the incident angle is 0, that's why the refracted angle is also 0. So any light ray that travels parallel to the normal line or perpendicular to the boundary will always continue to travel in a straight line. And the reason for this is because when the incident angle is 0, the refracted angle is 0. So what has this got to do with the semicircular block? So let's take a look at the semicircular block. Let's say this semicircular symbol represents the glass block which we will be using in our practical. So what's so special about this semicircular block? Now, if we were to aim the light ray in such a way that it will always travel towards the center of the semicircle, you'll find that the incident ray which is coming in from the air into the glass block will always be perpendicular to the tangent of the point on that circle. If you're wondering why, it's math. So you should recall what you have learned about circles in math. Any line that you connect from the center of the circle to the edge of a circle will always be perpendicular to the tangent of that point on that circle. So if I were just to draw some lines just to illustrate this, this is the tangent at that point on the circle. So the angle would be 90 degrees. So if this line was our incident ray, it would be traveling parallel to the normal line or overlapping the normal line. That means in this case, the incident angle would be 0, and therefore the refracted angle will also be 0 degrees. As such, you will find that at this point, the light ray traveling from air into the glass block will travel in a straight line all the way through to the other edge. So this only works, however, when you aim the light ray towards the center of the semicircle. So why do we want to do this? Because this way it enables us to control the angle of incidence of the glass block inside here before the light ray exits into the air on this other side of the semicircle. To show you visually, that means this would be the normal line, and this would be the incident angle at this point. By using the semicircular glass block and pointing the light ray towards the center of the semicircle, this enables us to control the value of this incident angle. This then enables us to observe the phenomenon of total internal reflection and therefore measure the value of the critical angle. So how do we get the critical angle? What we need to do is just adjust this light ray in such a way until the light ray that is emerging from the glass into the air, instead of refracting out, it should then be traveling along the boundary between the semicircular glass block and air like this. So at this point, we will then know the angle of this incidence would be the value of the critical angle. If you have forgotten what you've learned about total internal reflection, please watch my video on total internal reflection where you will learn in more detail this whole phenomenon of total internal reflection and what are the conditions that induce it. For now, we're just going to focus on the practical. So, some common questions. Why can't we just use the rectangular block to study total internal reflection? It may be possible, but the problem is with the rectangular block, we can't control the value of the incidence on this edge. That means it's difficult to control the value of the incident angle where the light ray is traveling from glass to air. And the reason for this is because the value of this incidence on the bottom here depends on the refracted angle above here, which depends on the incident angle in air. Now, we can of course increase this incident angle, which would then cause this refracted angle to increase. But the problem is this value is always going to be much smaller because it depends on the angle on this side. So remember that when light travels from air to glass, it always refracts towards normal. So the value of this angle is always going to be very small. If you're going to try to make this angle very big, it still won't be easy because no matter how big you make this is still going to be limited. It's still going to be quite small. So we can't make this angle very much larger. So that's why we use a semicircular block. This enables us to manipulate the angle to be as large as we want it to be. When using the semicircular block, do we always have to aim it towards the center? Can we not aim it at some other angle? If you do that, you won't get a straight line because if you were to aim the light ray like this, you can see now that at this point, the light ray is not parallel to the normal line. That means it has now reached this side at an angle, which would then cause the light ray to be refracted, and that will give us the same problem that we had with the rectangular glass block just now, where we have very little control over the incident angle on the other edge. So that's why we don't aim it randomly in the semicircular block as well. We always aim the light ray towards the center, the semicircle, because that way the light ray will travel in a straight line due to the incident angle and refracted angle being 0. And therefore, this enables us to manipulate the incident angle on the other side easily. So now let's take a look at how to use the glass block in a real-life practical so that we can measure the critical angle.
For this experiment, we are going to need a semicircular glass block, a piece of white paper, ray box with the power supply, and if you'd like to measure the critical angle, a protractor and a pencil. First of all, let us observe the phenomenon of total internal reflection. So we have our ray box connected to our power supply unit. So we switch it on to make sure that the ray box works. The ray box should have a filter that allows only a single ray of light to be emitted. Now, it's not very clear when the surrounding is bright. So what we're going to do is we're going to switch off the room lights. So over here we have the single ray of light, and here is the semicircular glass block. So when we shine the ray of light through the glass block like this, you can see that it travels in a straight line without deviation. As we turn the semicircular glass block, you can see that the light starts to change direction after passing through the glass block, and you can see there's also some light that's reflected. The reason for this light reflection is because every time light refracts, a little bit of the light is reflected back. As we keep rotating the semicircular glass block, you can see how the angle of refraction keeps increasing while the strength of the light reflected is also increasing. You'll come to a point where the light ray now is 100% reflected back into the glass block and out into air. Again. If you'd like to measure the critical angle of the glass block, here is how you do it. Now, first of all, we're going to trace the semicircular block on the piece of paper. Next, what we're going to do is we're going to use a ruler to measure the straight edge of the block in order to find the center. You can see it's approximately 10.2, so the center should be about 5.1. So that's about here. Now, why we want to do this is because we want to find the center of this semicircle. If you recall your math, any line that you connect from the center to the edge of the semicircle will always be 90 degrees to the tangent of the curve. So this is important because what we're going to do is we're going to aim the light ray towards the center. So the reason why we want to find the center point is so that every time we shine a light ray towards the center, as it enters the glass block, therefore the incident angle will be 0, and therefore the refracted angle will also be 0. So if we were to aim the light ray directly at the center point, this means that this light ray will then enter the glass block at an angle that is 90 degrees to the tangent at this point. This will be parallel to the normal line, which means that the incident angle will be 0, and therefore the refracted angle will be 0. So if we were to place the glass block here, you can see that the light ray travels in a straight line without any deviation. So we're going to switch off the lights for clarity. As you can see, the light ray has traveled in a completely straight line without any change in direction. Now, what if we were to change the angle where it is entering? So as long as we shine this ray of light towards the center, as you can see over here, okay, we're shining it towards the center. In case you can't see it, here's a semicircle. Let's shine the light ray towards that center. we'll replace the glass block over the tracing. And you can see how the light ray now has refracted, but it's coming from the center. Let me just shift it so that you can see it. So you can see how the ray of light is now coming out from the center, which means although we can't see the ray of light traveling in the glass block, it's traveled straight to this point, and that's why the light is exiting or emerging from that point. So no matter how the angle is, as long as we shine it towards the center, you can see that the ray of light will always travel in a straight line from air into glass towards the center point. The bigger the angle of incidence, the bigger the angle of refraction. You can also see that every time light refracts, some light is reflected back. So that's also a natural phenomenon. Every time light refracts, a little bit of light will be reflected back. So if we start again from here, where the incident angle is 0, as we increase the angle of incidence, you can see that the angle of refraction has increased, and so has the strength of the reflected light ray. You'll come to a point where the light ray suddenly is no longer refracted, and 100% of the light is now reflected back into the glass and out into air. To find out the angle at which this occurs, which is the critical angle, we need to position the ray of light so that the refracted light comes out at 90 degrees. So it's very faint, but it's just about here. So as you can see, just when the light seems to disappear, that's where the angle of refraction is 90 degrees. So using a pencil, we are going to make markings along the middle of this light ray. So that means this light ray will be the incident ray, and we're going to measure the angle to determine the critical angle of this glass block. So now that we have the light ray, we're going to use our ruler to connect the dots. We're going to connect the dots to that center point. I think that because the light ray was a little bit thick, it was not easy to get an accurate line. So I'm just going to draw the best fit line between those points. We also need to draw the normal line. So using a protractor to get the normal line. So that means at 90 degrees. So this line represents the incident ray which came from the ray box, which entered the glass block and exited at an angle of 90 degrees for the angle of refraction. To determine the critical angle, we need to measure this angle. So this will be the critical angle. Using our protractor, we're now going to measure that angle. And based on this activity, we can see that this angle we obtained was approximately 44 degrees. And that is the demonstration of the practical of total internal reflection using a semicircular glass block and a ray box. So I hope you found this video educational and helpful in understanding a little bit better about a practical to study total internal reflection of light using a semicircular glass block. Don't forget to click like and subscribe for more lab experiment practical videos by your physics teacher, Ms. Ho. Happy studying!